Hello everyone, this is the third edition to the matrix decomposition series, and today we'll be looking at the Cholesky decomposition. This is a special case of the LU decomposition and is done for positive definite matrices. Recall that a positive definite matrix satisfies the following properties. It is a n by n matrix, so a square matrix, and it's positive definite if and only if it is firstly symmetric, which means it's equal to its transpose. And secondly, given a vector of length n, the scalar x transpose ax is always positive, and it's zero only when the vector x is the zero vector. Alright, so the overall goal of the Cholesky decomposition then is to take this positive definite matrix and then decompose it into a lower unit triangular matrix and times its transpose. And recall that unit triangular just means that there are ones on the diagonal. You can almost think of this as taking the square root of a positive definite matrix, kind of like how you can take the square root of positive numbers. So the general procedure for this decomposition is as such. We will begin by simply finding the LU decomposition of our matrix A. Then we will further decompose U into a diagonal matrix D times a upper unit triangular matrix V. Now it turns out that for symmetric matrices, this V matrix is actually just equal to L transpose. And this gives us the following factorization. The next step is essentially to take the square root of the diagonal matrix D, which is very easy to do. And then we have LS times SL transpose. If we let G equal LS, then G transpose is actually just the second part of this factorization, SL transpose. And this is the Cholesky factorization, G times G transpose, where G is a lower unit triangular matrix. As you can tell, there are a lot of steps, but they're pretty straightforward, and let's see how they work in an example. We'll be decomposing the following positive definite matrix, and we can actually verify that this is indeed a positive definite matrix while we're doing the Cholesky factorization. Let's first begin by finding the LU decomposition. I'm going to simply let this scene play since I have a whole video on finding the LU decomposition, so check out that video if you're unsure on what's going on. Alright, now we can go ahead and find the D and the V matrix from U. The D matrix is really simple. It's just the diagonal entries of the U matrix. Notice that all the diagonal entries of the D matrix are positive. This means that A is indeed positive definite. Now we're good to proceed with the rest of our factorization. The V matrix is just U, but each row is going to be divided by the pivot value. Hence, we divide the first row by 1, second row by 1, and the third row by 4. Alright, now what you should notice is that the V matrix is simply L transpose. This is another check to make sure that you're on the right track with your decomposition. Now all we need to do is break down D into two matrices, namely S. We do this by simply taking the square root of each of the diagonal entries to get the diagonal matrix 1, 1, 2. You can verify pretty easily that this is a valid way to break down the diagonal matrices simply by multiplying them, and you'll see that you get back your original D matrix. Alright, so now we have LS and we're ready to find our Cholesky matrix G. Recall that G is simply L times S, and there we have it. Now you can verify that G times G transpose is indeed our original A matrix. And with that, we are finished with the Cholesky factorization. That's all for today. In the next episode, we'll be going over the Gram-Schmidt process for the QR factorization.